Hello everyone. Today we have the pleasure to have Professor Mathias Schacht telling us something about canonical colorings in random graphs.
All right. Thank you very much for having me. So it's a lot of fun to be in Korea. It's my second time, so I was once here 10 years ago, and so memories, of course, are already a little bit blurry after 10 years, and it's nice to refresh them. And I certainly enjoyed it a lot the last few days I'm here. And when I thought about what to talk about here, I saw that there's a structural group and there's an extremal probabilistic group, and maybe most of my topics are more on the extremal probabilistic side. But I tried to pick this talk because at least sometimes I can talk about something which I would say is also structural. But I'm afraid it's a little bit different structural theory than what the structural group is. So don't get your expectations too high. But anyway, so before I as we say in German, I talk myself about head and neck. So let's just start. Okay, so I want to talk about canonical colorings in random graphs. So this is tries to combine Ramsey theory in the setting, or tries to move Ramsey theoretic questions in the setting of random discrete structures. And I put here up the pictures of Erdős and Rado, who maybe proved the cornerstone theorem in canonical Ramsey theory, and we will talk about it on the way. And I, of course, should say this is all joint work with Nina Kamchev, who was visiting Hamburg for some longer time, and she is now in a position in Zagreb. Okay, so let's start with Ramsey theorem. So I like this to use this arrow notation, which was introduced in Ramsey theory already in the 50s and 60s. So we will write G has a Ramsey property for graph H or hypergraph H for R colors, and then we write G arrows H with R. And what does it mean? Well, it just means that for every R coloring of the edges of G, we find a monochromatic copy of H. Okay? And there's some ambiguity what means monochromatic copy of H. So sometimes people are interested in only induced copies and so on, but here it won't matter so much. Just let's think about a normal copy. But of course, when I say normal copy, then you may wonder why do I talk about G and H, because then usually it's enough to ask this question for cliques. But anyway, so for my talk it will be a little bit better to have a slightly more general definition. Okay, but of course, when you study Ramsey theorem in the first, in some first combinatorics course, then usually H would be a clique, and you would just say there's a sufficiently large clique Kn, such that for every R coloring of the edges of Kn, you find a monochromatic copy of Kn. So, and this is just kind of the straightforward generalization. Of course, there are many Ramsey type results in other setups. Maybe let me just brush over it. And then there's also several versions of what you color. I mean, so these are maybe the host structures and what you are interested to find, these things here. But then you can also vary the theme by maybe not coloring edges, but you color vertices, or you go even stronger, you want to color subgraphs and want to find a subgraph where all its subgraphs are monochromatic and things like that, right? So this is kind of was all considered over the last couple of years. I mean, couple decades. Okay, so I would like to maybe before we go too much into my topic, just to say maybe my view on Ramsey theory, or what I consider maybe the three major branches of Ramsey theory, which I learned or I was told. The one which usually gets a lot of attention is that you want to know properties about of some quantitative perspective, how large is G compared to H and R, right? So this is obviously you get, if you ask for the number of vertices, then you immediately get for Ramsey numbers. And of course there were a few breakthroughs last year, so in some sense we are living here in exciting times after a long, very slow progress. There were some big progress last year for different Ramsey number questions. And there were other questions that you ask for the minimum number of edges such a graph G can have, or if the graph is minimal, what is its minimum degree, and all these type of of quantitative aspects were studied. A second, and this is brings me to structure, is more a structural perspective. So if you look at this general statement in the terms with G and H, maybe maybe you want to know what are the subgraphs of G, right? So how does G look if it has the Ramsey property for H? And for example, one of the very first questions in that direction could be, can I maybe have such a G where the copy of H will be induced, which was answered in the 70s by 3 groups of authors. And another thing is kind of what I already mentioned, is what are the minimal substructures, which are the unavoidable substructures of G in order for G, which must appear in any G which has a Ramsey property for H. Right? And there was some questions of this type. So for example, motivated by the trivial example that the Ramsey number for the triangle in 2 colors is 6, people were asking, is there a graph which has this property and doesn't contain K6? Or is there one which doesn't contain K5? Or is there even one which doesn't contain K4? So is there one which only has clique number 3 itself? And this was answered first in a special case by Vogtmann, and then in a very strong way by Rödl and Ruciński, who showed that in fact you can keep these 2 invariants the same. Okay, so you can keep, you can have the Ramsey property under the assumption that the clique number of G is the same as H. Right? So there exist Ramsey graphs which have the same clique number. You don't have to need any larger cliques. Okay, and then the next question, which was also investigated, or is also kind of fairly interesting, and I will say just a little bit about that, is obviously if you have the Ramsey property for H, you must contain copies of H, and you must of course contain many copies of H, and of course they have to intersect on edges, because no other way you can get monochromatic copies of H enforced. If they would not intersect on edges, then basically you could just color in every copy one edge the way you like, and another edge the other color, and you will never find a monochromatic copy. So the only way to get this Ramsey property is copies of H must heavily intersect on edges, kind of. And the question is that enough? Right? Do you need more? And why is it plausible that such a thing could be true? Well, you could compare it with Erdős theorem of the existence of high chromatic graphs and large girths. So it tells you that there are, in fact, if you go back from edge coloring to vertex coloring, and the monochromatic subgraph which you want to have is just the trivial thing you can think of, it's just one edge, then it's in fact true that there are graphs which have high chromatic number, which means if you color them with R colors, you still find a monochromatic edge. And locally, all you find are trees. So you only find edges which intersect in vertices. Okay? So this is kind of, it answers in some sense, in a full way, this question, if you would say H is just an edge, and we consider vertex colorings. The answer would be yes. The only thing you can find is that these copies intersect in vertices and they don't create any larger structures. The only substructures they form are trees locally. And this was kind of also answered for hypergraphs recently by Rödl and Rado last year, where they proved that if you consider edge colorings, then locally all you will see are kind of tree-like structures of copies of H and G. There's a Ramsey graph which doesn't have short cycles of copies of H. Now, what means a short cycle of copies of H, maybe this should not be my topic of the talk. All what I want to say is kind of these are maybe, is the structural perspective on Ramsey theory. So if somebody says he does, or he or she does structural Ramsey theory, then maybe these are the type of questions they're interested in, and this is a field where there's also large activity in recent years. Okay, and so I will not talk about these things too much, a little bit about this. So what I will rather talk about is, and this was also a research theme which came up in the 90s or late 80s, is that you study it from the perspective, when does the random graph has a Ramsey property for H? So you want to know if the threshold for this property. And this threshold exists because kind of this is obviously a monotone property. If I have more edges, I cannot destroy the Ramsey property. So there is some threshold probability when the random graph G and P will have this Ramsey property with high probability. And of course, it must be non-trivial because the empty graph doesn't have the Ramsey property. Okay? And I will a little bit now talk about this. Okay. Yeah, so if there are any questions, so then just stop me anytime. Okay, so this explains one part of the title. The second thing is I should talk about is canonical coloring. So what are now canonical colorings? And this is just that we move away from a fixed number of colors. Okay? So what happens if we allow an arbitrary number of colors for coloring the edges? And of course, it's rather immediate that in that situation you cannot look for monochromatic copies anymore because the enemy or the person who colors the graph could just do an injective coloring. For every edge it uses a different color. So I must be prepared to also be happy with such copies. But those copies are maybe rainbow, and maybe I'm happy with them. There is something else what you can come up with in order to avoid monochromatic copies and also to avoid rainbow copies. And that is basically you can order the vertices and the first vertex decides the color of the edge. Okay, let's say you order the vertices 1 to n, you want to color the edges of kn, you order the vertices 1 to n, and if you have the edge ij and I is smaller than j, then the color of the edge is I. Okay, so this way you would get monochromatic stars to the right if n is to the right and 1 is to the left. And this, of course, you can also do backwards. And those colorings are clearly not rainbow because not all edges are different, and obviously you don't have monochromatic copies if you are interested in something more interesting than a star itself. Right? And those colorings, maybe then I would call min-colored or max-colored. Yeah, you could have other names, lexicographic colored and so on, but I think min and max is easiest to remember. For hypergraphs, the thing is a little bit more general. Let me just quickly mention it because sometimes, yeah, this is I think not always taught, but I think it's good to know anyway. So if you have a k-uniform hypergraph, then there are 2 to the k different canonical patterns or patterns which you can get in similar ways. And the right generalization of all these 4 patterns, rainbow, monochromatic, min and max colored, is this concept. So you pick your favorite index set of the set 1 to k, so this we call I. And now 2 edges have the same color if and only if you pick the vertices after they are ordered with the indices from I, and then they have the same color if they are the same on these vertices. Okay, I think I said it a little bit in a convoluted way. So one more time, so you have the edge U1 to UK, and you have the edge W1 to WK, and maybe in the index set you fixed some indices, and you allow these 2 edges to have the same color if and only if UI and WI is the same for every I and I. Okay, so just so that we understand that we are on the same page, so this min-colored thing would be corresponding if you take from the set 1, 2 just the element 1. Right? So then they would have the same color if they agree in the first vertex. Okay. Max colored is also easy, then it must be the set which only contains 2. And now one has always a little bit to think about. So the empty set, which would mean it's always true, kind of then this would be void, so then this must be the monochromatic copies. And the set 1, 2, that the colors are only the same if it is the same edge, if both vertices are the same, then this is rainbow. Okay, so this is how you get these 4, monochromatic, rainbow, min, and max colored as subsets of the set 1, 2. Okay, does that kind of make sense? Okay. Okay, and this is, so these are all the patterns. And as you see here, this only makes sense if the vertex set of the underlying hypergraph is ordered itself. And so from now on, if I don't say it, so I will always assume that the vertices are kind of numbered 1 to n or whatever. Yeah? Right, and so Erdős and Rado, and that's why I put them on the first page, they showed that if you color the complete graph or hypergraph, then you always find a clique which is canonically colored, and if the clique you start with is large enough, you can enforce any large clique you like. Okay? So this is what they proved in 1950. I would state it then this way, so I still put this arrow notation, but now I put the star on top of it that I'm only looking for canonical coloring. And of course there's no number of colors anymore. One thing which is kind of important, especially when you think about things different than cliques, but already for cliques it matters a little bit, is that both are ordered, and I look for ordered copies. Of course, for clique, ordered copy, I mean, the copy is there, but I'm not allowed to reshuffle the vertices. Okay, so why does it matter? If you think about the triangle would otherwise be always canonically colored, right? So if I have a triangle and you color it, either it will have 3 colors, then obviously it's rainbow, or it will have 2. If it will have 1 color, then it's monochromatic. And if it has 2 colors, I could pick the vertex which has the 2 edges which are incident to the same color and make it the first or the last one. Right? But this is not. We don't allow that. Okay. So there are, in our world, there are colorings of the triangle which are non-canonical, and these are the colorings which look like this. If this is the ordering of the vertices. Okay, so this is a non-canonical copy. Okay, and that's why kind of it's important kind of to just fix the concept. Both are ordered, and I just look at ordered embeddings. Okay, which good. Maybe a little bit about how Erdős and Rado proved it. So they used Ramsey's theorem. And for that, of course, you have to bring the number of colors down. And the way they did it is they looked at sets of size 2k. And then they looked at the color pattern they found on these subsets. And this is a finite number. It only depends on kind of k and the number of colors you have. Basically the number of partitions you can form there, and then they applied Ramsey's theorem for 2k uniform hypergraphs for that number of colors, and then you can show that if you have a large monochromatic clique, only these canonical patterns don't create conflicts. The other one at some point it just doesn't fit, right? And also because you can, if it's that large, you can take one edge and the other edge, put them in, and kind of compare how the colors are, right? And this way you can kind of transport the information through the whole hypergraph. So this is why we take 2k subsets. And the lower bound, I mean, and of course this tells you that the upper bound is exponentially iterated 2k minus 1 times, because this is kind of the Ramsey number for 2k uniform hypergraphs for many colors. The lower bound is only that you just use the normal Ramsey lower bound for essentially L colors. So if you don't want to have a canonically colored KL, basically what you say if I forbid monochromatic and the number of colors is fewer, then I can have a canonical where every vertex determines the color, then I cannot have any canonical copy. Right? So I just have too few colors. And this gives you a lower bound of this type, and of course there's a huge exponential gap between them. I mean, the number of exponentiations is kind of fairly different, right? So it's essentially k. And this was closed, this gap, in the 90s. So there was some work of Lessmann and Rödl where they showed that in fact the lower bound is the correct one. So for graphs, the lower bound is exponential, and they found a proof which avoids using full uniform hypergraphs, and also got an exponential upper bound. And I will show you kind of some streamlined version of that proof later. And Scheler actually proved that for hypergraphs, the lower bound and the upper bound are of the same order of magnitude if you consider the same number of exponentiations as the same order of magnitude, right? Of course, the functions in the exponent are different, but maybe that's too much to ask for. Okay, what is maybe interesting is that if you look careful in the graph case, then the lower bound is the order 2 to the L squared, and the upper bound is of order 2 to the L squared log L. And the reason is precisely because here you take essentially the L color Ramsey number for KL, this is the lower bound, and somehow you cannot exploit a more kind of interesting coloring where you also take kind of into account maybe to have kind of just, I mean here you just argue I don't have enough colors and I don't have monochromatic, and that's why I'm done. So it feels that this lower bound is not maybe the right one, kind of. It seems a little bit too simplistic if I just forbid monochromatic copies of KL. And for the rest I just say I don't take enough colors. However, it's kind of a very hard and long open problem to understand that better. And for example, the question whether this log L is needed or not is kind of, it's considered a very difficult question. Okay. Okay, so now we have seen normal Ramsey theory and canonical Ramsey theory. Now we have to bring it to the random graph. So in the random graph, I already mentioned a little bit, one of the main results let me state it in the special form for cliques, goes back to Rödl and Ruciński also from the 90s, and they determined the threshold when the random graph has a Ramsey property for KL. And I stated it, maybe I forgot to put the number of colors, but yeah. So it doesn't matter. So if the edge probability is asymptotically smaller than n to the minus 2 over L plus 1, then it is true that you can two-color the edges of the random graph without a monochromatic copy. So I mean, of course, if you're interested in the threshold, you have to prove the 0 and the 1 statement, and the 0 statement would mean that you don't have the Ramsey property, and if you can avoid it already with two colors, then of course you can also avoid it with more colors, right? So that's why it's enough to consider the two-color case here. And it tells you, okay, so if you color the edges on the random graph, this high probability has the property that you can color its edges without creating a monochromatic copy of KL if P is asymptotically smaller than n to the minus 2 over L plus 1. In fact, you can prove a little bit more, so you don't really need asymptotically smaller. You can put the small constant C in front, but maybe for this talk it doesn't matter.
So there's no dependence on number color.
Yeah, I mean for the 0 statement it's not so surprising, because there you could just say you just have to find a 2 coloring, and this is maybe kind of good enough. Also, if you allow me to use more colors, I can just use 2 if I want. Right? Mm-hmm. But you say it could be different. The threshold could depend on R, and maybe this is what the theorem tells you. No, it doesn't depend on R. So the R only tells you, if you would write it with constant, how large these constants are here. And the upper bound, the 1 statement, which is maybe also the more interesting part of this theorem, tells you that if P is asymptotically larger, or in fact just a big constant times this, and then the constant depends on R, then no matter how you color the edges of the random graph, it will have the Ramsey property. And this is, for example, so this is kind of interesting in several ways. Maybe let's a little bit talk about why this is a reasonable threshold and not just some arbitrary edge probability. So the point is, and this is kind of, you can view as a heuristic argument for the lower bound, if P is smaller than that, this is precisely the point where the number of edges and the number of copies meet. Okay? So what do I mean by this? If P is asymptotically smaller than this, then the expected number of copies of KL in G and P is asymptotically smaller than the expected number of edges. Okay, so basically you just write, I mean the clique is balanced enough that you really just have to do the expectation for the clique itself. So if you write p to the L choose 2, n to the L, and you compare it with p n squared, and you say for which p this is equal, then you come up with precisely this number. Okay. So this means if you are smaller, so I'm now explaining how this two coloring you should think about it. You should think about the auxiliary hypergraph where the KLs are built on the edges of G and P. So what do I mean by this? So the vertices are the edges of the random graph, and the copies of KL, they are the edges of the hypergraph. So this hypergraph is L choose 2 uniform and has P and choose 2 edges. Okay. And if this hypergraph, I mean, the number of edges is the number of copies of KL, the number of vertices is the number of edges. So then this inequality tells you that this hypergraph has fewer edges than vertices, right? And this usually means, if this happens in a uniform sense, that you cannot have any cycles or short cycles, or only very, very few cycles, right? So this hypergraph is very tree-like. And if it's tree-like, then you can two-color it without creating a monochromatic edge. But this means you two-color the edges without creating a monochromatic clique. Okay. Of course, this is not the full proof, but this is just a heuristic. What happens? Okay. The upper bound. For the upper bound, the paper was based on an inductive argument, and the induction was along the edges. So it was the proof of this one statement was done for all graphs, not only for cliques. And then it was an induction on the number of edges and the number of colors. And there was some kind of, you could say color focusing argument. So you expose the random graph in 2 stages. In the first stage, you know by induction assumption that you find many copies of the graph edge with one edge removed. And then it happens at this threshold probability. That means that many pairs are now closing those monochromatic copies. And then you show that these pairs are rich enough to host a lot of copies of H itself, but now on them one color is forbidden, and then you can iterate. This is kind of very rough overview sketch, but this is kind of how this proof went. Okay. Good. So maybe a few remarks. So the one statement had some influence. So there were some generalizations were discovered. So it turned out that that this proof was not so easy to extend to hypergraphs. So original one from Rödl and Ruciński, and but then for hypergraphs it was developed about 15 years ago. I mean, on this slide, don't look at the years when this paper appeared, because they partly appeared with lots of gaps and so on. About 15 years ago, there was this transference principle developed by Conlon and Gowers, and which allowed them to transfer such Ramsey properties and experiment properties from the traditional setting to the random setting at this 2-density threshold, which has the same heuristic argument which we just have seen. And this worked the same way for graphs and hypergraphs. And there was some other approach on some multi-round exposure approach, more closer to the original argument of Rödl and Ruciński, which we had together with Friedgut and Rödl, where we could also transfer this one statement to hypergraphs. Then in a few years later, these hypergraph containers were developed by Sexton and Thomason, and by Ballock, Morris, and Samotti. And from those fairly general results about independence numbers in hypergraphs, you can you can also transfer these Ramsey properties fairly easily now. So if you believe in these hypergraph containers, or if you use them as a tool, then it's kind of a very short consequence. There was something in behind. So for example, if you can transfer the regularity method to subgraphs of the random graphs or the subgraphs of random hypergraphs, then you can also transfer these results. And this was also partly done at the same time. And yeah, so as I said, so these approaches extend more straightforwardly to random hypergraphs than this original proof of Rödl and Ruciński. There's another question which we a little bit glanced here, and that is, you could of course ask if the threshold is determined, and after I told you, you don't only need this asymptotic gap between for the zero statement and the one statement, you can have it with constants in front of this function n to the -2 over L plus 1. Maybe you want to know, is it possible that these constants are arbitrarily close to each other? So in other words, you want to know whether the phase transition, the window of the phase transition is smaller than the asymptotic order of the threshold. And this can be done for these in the graph context. So there's some important work by Friedgut, Rödl, Ruciński, and Tatali, where they did it for the triangle and two colors, and that was kind of some fairly complicated proof. And we could now extend this together with Friedgut, Kupperberg, and Samotti for cliques and more colors. Okay, so now let's get back to the question I want to talk about here. So of course, after you see this, that the Ramsey theorem is transferred, maybe it's natural to ask, can this canonical Ramsey theorem be transferred to the random setting? Okay. And then the question is the same heuristic still valid? And of course it is, because as we said, so if I don't find a monochromatic copy, then I can two-color without a monochromatic copy, then I cannot find a canonical copy, except I might be the triangle, right? But certainly for cliques larger than this, which have at least 4 vertices, there are no canonical copies with 2 colors, except monochromatic. So the lower bound from the Rödl-Ruciński theorem, the zero statement from the Rödl-Ruciński theorem, gives me automatically a lower bound here. So that means the threshold is at least a 2 density. And people studied a lot of questions. Is the bond statement true if maybe I restrict the coloring? So maybe very natural variant is you don't allow arbitrary coloring, but the coloring should be matching. The color classes should be matchings, and maybe then you can enforce a rainbow copy. And there was a lot of research on that. And then it often happened that in fact the 2 density, the threshold which we just have seen for cliques, also turned out to be the right one. So I think it was kind of believed, certainly I believe that that the same threshold also gives you this canonical property in GNP. And this is what we proved. Okay, so so with Nina, we showed that if you want to have the canonical property for KL, then you have to take the same edge probability. So n to the big constant times n to the -2 over L plus 1, and then you will have it. Okay. Good. As I said, so there were several related results, and there was some parallel work of either Rado, Koyakawa, Morris, and Mota, who proved a related result for cycles. The triangle is not only excluded for for these technical reasons, it's in fact, it appears earlier. And the reason is, if you have a K4, just one K4 in the random graph is enough to force a canonical copy of a triangle. So let's see, this is kind of easy to see. So if you have 4 vertices, and let's say they are ordered that way from left to right, and you tell me all 6 edges are present, but apparently there's no canonical triangle, well, as we have seen, that means these 2 edges, the lexicographic, the smaller, the first and the last, they must be the same color. Okay. This forces me, for example, that these 2 have the same color. But now by some transitivity, it also forces me these 2 to have the same color. And it also forces me this one and this one to have the same color, and I found a monochromatic. So kind of it's straight. Okay? So 1 K4 is enough. It even looks, for the moment you may think, did I really use all edges of the K4? But I did. And the K4 that it appears happens earlier. It happens with edge probability n to the -2/3. And this other parameter that we have seen would be n to the minus a half, which is kind of later. Okay. Yeah, as we already have seen, kind of, you could also now ask it if you want to move away from cliques. Then this lower bound of Rödl and Ruciński, it always works as long as you don't have a vertex cover of size 2. Right? So if you have a vertex cover, if you have two vertices covering all edges, then maybe if those would be in front, then you could have a canonical pattern of this graph image. Going back to the structural people, so Christian Reyer, of course, is my colleague, and he came into my office when we worked with Nina, and then he asked, so what are you doing? And we explained a little bit, and then he said, should I imagine it like this? You showed that there exists a Ramsey graph for this canonical property G, where cliques only share edges. So the KLs share only the minimum information, so they don't share triangles. And then we said, yeah, precisely, and so now we added it as a corollary. So there are kind of, it shows you that the random graph, in the random graph there will be only very, very few pairs of clique which share more than an edge, which share a triangle or something like this. And then you can easily remove them, and these Ramsey properties are robust enough that they don't go away by just such a small alteration. So this shows you that there exists a graph G which has a property that all KLs only intersect in edges, and it still has this canonical Ramsey property. Okay, so the proof is as follows. So let me say the main ideas. The main ideas is we found a proof which works in the graph context, in the normal context, fairly well, and that proof could be transferred to the random environment using the transference theorems of Conlon and Gowers. Okay, so this is kind of the high-level proof. But for that you need a purely graph, an argument which purely works in the graph world. So if you would do this, what Erdős and Rado do, you go through the hypergraphs, then at least to me it seems implausible that you can transfer it, because you would require way too dense substructures. Okay. And as I said, so this proof is inspired or is kind of a streamlined version of this proof of Lessmann and Rödl. And it also appeared in a paper by Allen et al. And I think in order to give you something which you can take away from this lecture and not to be showered down by the technicalities of the Conlon-Gowers transference theorem, I will tell you this proof. And then kind of, I think then, I hope you have some feeling of how this proof goes. Okay? So in case you wonder how one proves the canonical Ramsey theorem in the graph context, so this proof I will now show you, and then for the random graphs, in some sense, we transferred it to the random setup, and I can say a little bit more about it. Okay, so how does this proof go? And this proof is in some sense, yeah, so this is our blueprint, which then we followed in the random setup. This proof distinguishes the coloring. So somehow, if there are no restriction on the coloring, then you, of course, you have to deal with all of them. And in order to tame them, it is natural to classify them as follows. So we have a coloring of the edges of Kn. The vertex set is 1 to n. We don't know anything about the coloring, but let's say it's delta bounded if the monochromatic edges incident to one vertex, so the edges of the same color to incident to one vertex, is bounded by delta n. Okay? So vertex has n minus 1 neighbors, and if it sees at least 1 over delta colors, and kind of we require slightly more, no color appears more than delta n times incident to this vertex, then we are happy, and then we would say the graph is delta bounded. Okay? So that's the definition. And if you are delta bounded for some delta which is smaller than 1 over L cubed, then you will, what does it mean? It means you have lots of colors everywhere. So what are you hoping for? You are hoping for maybe for a rainbow copy, and that's in fact what we will show. Okay? So in order to to go for a rainbow copy, we count how many non-rainbow copies we will have. And of course, we know the number of all copies, and that's basically it. Okay, so how can we have a non-rainbow copy? Well, one thing which we could have a monochromatic sharing, right? So it could happen to us that somewhere I have this 3 vertices like this, and then of course there's no chance that they are in a rainbow KL, so we have to avoid it. Okay. But since if I fix this edge and I want to fix another red edge, then I only have delta n choices for this vertex. So this means the number of these triples is bounded by something like delta n cubed. Okay? Just by this boundedness property of the coloring. Okay, the other bad thing which we could have two edges which are non-meeting in a vertex, and they also have the same color. Of course, this can happen from time to time. But since I'm delta bounded even on the vertex level, I'm delta bounded globally, right? So if every vertex sees every color at most delta n times, then no color can appear more than delta n squared times in the whole graph, okay? And that means as soon as I fix this edges, I only have delta n squared choices for that one. So that tells me I have only delta n to the 4 such quadruples in the whole graph. Okay. Okay. And now basically what you do is you just pick a random subset, and you will have so few copies of these inside that you can remove vertices, and then you get a then you get a rainbow copy. Okay. So basically what you do is you pick a random subset of size 2L, and then you will have fewer than L copies of those, or L copies of, together you will have fewer than L copies of those, and for each of these copies you remove one vertex, and then you have a rainbow K. Okay? And in order to do this calculation, that's where you come, where you get this restriction, delta has to be smaller than 1 over L cubed. Okay, so, but this is kind of a straightforward calculation, but you need kind of what sometimes it's called the deletion method. Okay. Okay, so that means in the delta bounded case, you are done. So now, if you are not delta bounded, then you feel kind of at home. I mean, at least in the Ramsey theoretic context, let's say. Yeah, so if you put it on the internet and I would show my daughters and they would hear that I feel at home when I find a non-delta bounded column, maybe they would worry. But I think the probability that they would look the video so far is low, so I think I won't show them. I'd show them, look, your father's on YouTube. And then said, okay. Did you watch the video? No. Okay. But among us we can feel at home, and the reason is clear, right? So if you have one vertex, and so if you are not delta bounded, that means you have one vertex, and this vertex has many monochromatic neighbors. And of course, I don't know where this vertex is, to the left, to the right, are the neighbors to the left, to the right. But without loss of generality, I can say I have a subset of size delta n over 2. Such that all edges go in the same direction and they have the same color. And now I can look at this induced subgraph here. And I know again, if I'm delta bounded, I find a rainbow clique inside. Right? So this is what we just proved. And we are back at case 1. Of course, the numbers shrinked a little bit, but we will find it inside. So that means also inside I'm not bounded. And what does that mean? That means I have somewhere a vertex. Maybe now the neighborhood goes the other way. But it will still have size, whatever. Let me put it here. Delta over 2 squared times n. And I continue like this. Okay. And this means I so what I do is, and that's what I meant with being at home, I do this normal standard proof of Ramsey's theorem with the color focusing. It's a little bit more tricky. I have to watch that I go left and right. And of course, I may pick up more than just 2 colors. Right? But if I do this 2L squared times, then I can use once the pigeonhole principle to make sure that I always went to the same direction. And then if I have it L squared times, either one color repeated L times, or I have no color repeated L times, but then I have a rainbow a rainbow copy. Then I have a min copy, right? So if one color repeated L times, then I would have a monochromatic copy. And if I went to the right, and I have somewhere L vertices where the color was different, I mean actually L minus 1 vertices is enough, then I would have a min color. Right? So this is the proof. And I think this is what I wrote here. Okay. Right. So this is kind of the blueprint of the proof. Of course, in the random environment, this it doesn't work so that you can go one by one after this, right? Because, for example, implicitly here you said that the 2L squared neighborhood of a vertex is non-empty. So you went to the neighborhood 2L squared times. When we look at the random graph at the edge probability as I proposed, after already L over 2 steps, the neighborhoods are typically empty. So in that regime, you cannot find a clique KL. You can only find cliques of size L over 2 by going through vertex neighborhoods, because then otherwise they are typically empty. Right? There are only too few of these cliques. So that's why you have to deal, you cannot only work with one copy not to be bounded, but you need many vertices violating this copy and kind of have to kind of keep them and carry a more global structure in order to imitate this proof. But kind of this is maybe really technical or kind of some technical details, of course, which took us some time to figure out. But in some sense, whenever we got stuck, we looked at this proof and tried to kind of find the reasonable answer in the random setup, right? Okay. So in the remaining 5 minutes, let me talk a little bit about some open questions. Yeah, so if you think about it in the general case, then it might happen that the ordering of the graph may have some influence on the threshold. Okay. So what do I mean by this? So it could be that if you want to have a canonical copy of C4 ordered this way, might have different thresholds than canonical copy of C4 ordered that way. I think it's not so likely that this will happen, but it's not known, kind of, at least not to me. This could happen. Then, of course, maybe it would be nice to figure out whether this, what is called the two density. So this is the point when the expected number of copies of the graph and all its subgraphs are at least as large as the expected number of edges. This parameter is called kind of, so it's 1 over the 2 density of H. If this is always kind of leads to the threshold. And yeah, so in general. And of course you could ask what happens for hypergraph. And there I was told that Morris, Cooper-Wasser and Samonti kind of know such a proof where they use these the container theorem in a more direct way to transfer them. Of course, you can canonical Ramsey theorem theory is maybe a little bit forgotten, but it was kind of a big topic in the 70s and 80s. Kind of for any type of Ramsey theorem, people then wondered what is a canonical one, what is it for Van der Waalen, how is it for multidimensional Van der Waalen, how is it for Head-Jewett, and so on. And of course, for some of these structures, you could also ask, can you bring it to the random setup? And there's something for Van der Waalen. I think there was some announcement by the group in Sao Paulo that they kind of could do it. And I think there is currently some interest in such things. The last thing which I wanted to mention is maybe a little bit needs a little bit of explaining. For these canonical Ramsey numbers, you could still ask some more refined question about its growth. So I talked about it at the beginning of the talk a little bit when I said, well, Erdős and Rado used Ramsey theorem for 2k tuples in order to get the upper bound was large gap, and then I said same exponential gap was obtained by Scheler, right? But this is always that you say you want to have a canonical copy of your clique of a given size. But of course there are, structurally, I would say, canonically different patterns. So for example, the way as we talked about it, right? The index set I will tell you what canonical pattern you want, and maybe you want to allow different sizes for different canonical patterns, right? Like an off-diagonal Ramsey number in that sense. So for example, you want Either you want to have monochromatic of size L0, or maybe you want min of L1, or you max also of L1, and maybe rainbow of size L2, right? So you could ask such questions. And if you think about this, then this makes already sense in the one uniform case. Okay, so let's say the canonical Ramsey number for one uniform, what is this? You just color vertices. And what are the canonical pattern? Well, you could have monochromatic or rainbow. Let's say, and then we all know this is essentially this Erdős-Rado, right? So we used this a couple minutes ago. Let's not, it doesn't matter whether this is, I mean, we know it even more precisely, but let's kind of say it's kind of a disorder. Right? And if you go through the proof which I just showed you for graphs, then we have 3 patterns, as I said, or 3 types of patterns. We have 4 patterns, but I would say 3 types. We have monochromatic and rainbow, and we have maybe min-max. And let's say those I want to keep the same number. They should be symmetric, right? And if you look at this proof, which we have just seen, then it gives you an upper bound which is of the form L2 to the L0 times L1. Yeah, so if you look at closely, then there will be a 6 here. Right? And this is also why the general bound, I told you the general upper bound is 2 to the L squared log L, right? So if all these L's are the same, then this is 2 to the L squared log L, right? Okay, so now the question is how to generalize this. And a very naive idea could be that for 3 uniform hypergraphs, then you would get this. Okay, so if you would say you quantify the size of the clique, either that the pattern is given by monochromatic or by rainbow, or the vertices determine the color, first, third, or third, or the pairs determine the color, then maybe such a formula could be true. At least in the symmetric case, it would match the bound of Scheller, so it's not completely far-stretched. On the other hand, I mean, I think there are many other ways to generalize this, so I think it's kind of just numerology, but anyways, why not? Good, so that's maybe where I should stop.
Thank you. Any questions?
Do you believe the canonical Ramsey program has the Schacht's threshold?
Have what?
Schacht's threshold.
Yeah.
I mean, the one with where the K4
I
was
could,
indicated
why
or
not? I mean, I think, there are certainly monotone, fairly natural monotone property. And since these Ramsey properties, the normal Ramsey properties have a sharp threshold, kind of I would, without having thought about it too much, I would think that they could. The only thing what is a little bit problematic, so or why I would be a little bit shy, so I wouldn't kind of maybe bet too much on it, is the following. So in order to have the sharp threshold, then the one way you can think about it is if you're already close and you don't have a monochromatic copy in the finite and the bounded number of color cases, that means that the coloring is very, very, very restricted. And that means by a few random edges already kind of can enforce a monochromatic copy, kind of. That's why you cannot hold it, and that's why the threshold is sharp, kind of. Or this is maybe one way how to think about it. If the number of colors and everything is unrestricted, then those arguments are much more kind of, it's not so clear what structural property should capture the notion that there are only few of them close to the threshold, and that would make me kind of a little bit nervous.
Yeah, there are different notions for sharp thresholds. What maybe the easier notion of Friedgut, can this theorem be applied here?
I mean, this is all, I mean, the Friedgut theorem is the only one how anybody can prove a sharp threshold in this context. So even for these normal Ramsey properties, so everybody uses kind of this Friedgut criteria.
Yeah, so at one point you said the K4 was, the existence of a K4 was the indicator for the triangle.
Mhm.
So for this one, then probably not a sharp
No,
threshold.
then not,
So
yeah.
for this case.
Yeah, because it's just one it's not a global property, it's just local one copy. So then it's not sharp.
Any other questions?
You had this deletion approach. Do you think that's the most efficient way to do that, or do you think there might be?
There are in the paper of Allon there are constructions which show that if you follow this proof, kind of then this 6 is unavoidable. But there the deletion is kind of not the crucial part. The crucial part is that you have to pick delta to be smaller than 1 over L cubed. So this L cubed is kind of is one part. It's a half of the 6, and this is kind of and that I think is unavoidable if you look at that you want to forbid things on 4 vertices and you want to scale it with a number of vertices. So in order to get rid of those, and this is also kind of and there in that sense it's sharp. So there's a in that paper of Allon there is a result which says if you can color the edges of the complete graph by real edge coloring, meaning color classes are matching, so you are as bounded as you want. And the largest rainbow clique you can find is only of size third root of n. And this is kind of tells you that kind of there's not you cannot improve it much.
So is it true that the canonical Ramsey function is symmetric? So in the canonical Ramsey L0, L1, and L2, if we permute the L0, L1, and L2, then the number is still the same, or it may differ.
If they are this, what is the question? So if they are
all the same, then it is clearly the symmetric. But what if the L0 is the L0?
no, I don't think it's symmetric. I think because these are fairly different objects you are looking for, and this tells you that kind of so you can get much larger rainbow in some sense.
But L0 and L1.
L0 and L1, yeah.
I mean, you're claiming that, right?
Yeah, I don't know. Yeah, sure. Yeah, but I don't think it's symmetric in such a strong sense. And I'm actually I'm really, if I should be honest, so I think maybe I could imagine that inside L2, so these are the patterns which are determined by pairs. I could imagine that it matters whether you take the first pair or the last pair. That those are maybe symmetric, but if you pick the pair which is the long edge, that might have a different influence. So treating them all in one parameter might be a little bit too naive. And this you may only discover when you consider 3 uniform.
So this function p hat h is the threshold for making canonical coloring h, right?
And that
The main theorem so far is for the clique, right?
Right.
When h is a clique.
So we proved it for cliques, and we know it's not true for triangles. And the question is for which it's true and for which it's not true. And we know that it is certainly a lower bound whenever you don't have a cover of 2 vertices. If you have 2 vertices such that all the edges of the graph are incidences, so you are kind of K2T and maybe the 2 ones still have an edge. So those are the only ones where it could be smaller than the 2 density. Because otherwise there is already this lower bound if you put maybe trees aside. But it could be sometimes also larger than the 2 density. That we don't know.
Right. Any other questions? Otherwise, let's thank the speaker again.